Cool. Uh, so welcome to this session about Docker containers in Java. And it's basically highlight the things that we should know and the things that we should avoid while working with containers. And before putting your Java application inside the container and deploy it into production. So before jumping into the slides, a quick introduction about me. I'm Mohammed. I work for a DevOps company in Morocco called Xhub. And for those of you who don't know where Morocco is, it's basically it's in north of Africa, very close to Europe. And if you want to have a chat maybe after the conference, ask any questions maybe about Java, containers, Kubernetes, anything, please feel free to reach me through Twitter. That's the easiest thing. My Twitter handle is Laytoon, or send me an email. I'll be happy to answer. So this talk basically highlights the story of a Java developer and is completely an imaginary person, and it's called Farouk, and Farouk has been working with Java for a couple of years now. And Farouk truly believes in the power and limit of code, and he starts hearing about this cool new technology called containers, and he wants to start playing with it, see what benefits this new technology offer. So this talk basically highlights your journey, starting with somehow the philosophical question, is it a good idea to put actually a Java application inside a container? We will discuss afterward how to create effective Docker images for our Java applications that are both smaller, faster, and secure. We will see the tools and libraries that help us get up and running quickly while working with container. We will afterward discuss the things that we should know and the things that we should avoid before deploying our containers into production. And finally, we will see all the features that has been added to Java to make it more container aware. So nowadays, containers are everywhere, and they are used for a wide range of applications, like from small serverless application, from fast serverless applications to huge monolith enterprise application. And that's because containers offer great benefits. And one of the great benefits of containers, it offers like ease of deployment, backed by a huge and vibrant ecosystem that offers many tools and libraries and softwares that make managing containers into production a lot more easier. Containers also help us to solve many problems that we face into the cloud. And I don't know if you are familiar with the nosy neighbor issue. Anyone? So basically, the nosy neighbor issue is when you have your application share the same infrastructure with other applications, and those applications impact negatively your application since they are sharing the same resources. And during peak performance for those other applications, they impact the resources that your application need. So that's what we call the noisy neighbors. And containers helps to solve this issue, since it offers like resources limitations and resources optimizations. And that's because the building blocks behind the containers technology, and they offer this lightweight isolations that allows more dense packing. So, and the backbone technology behind this lightweight isolation are two things basically, and they are namespaces and cgroups. I don't know if you're familiar with one of those technologies, and those exist in the kernel of Linux, and namespaces and cgroups basically. So namespaces are used for providing a different isolated view of the system. So each process can have its own view on different namespaces like user ID, process ID, network ID, and so on and so forth. Cgroups, on the other hand, enables us to implement limiting and demeasuring for the resources that can be used by a process. So like memory, CPU, network IO, block IO, and so on. So in cgroups, each subsystem, which are memory, CPU, and block IO, network IO, form a tree structure or a hierarchy of nodes. And each process belongs to one node and one node only in each process belongs to one node and one node only in each. So for example, given a process, it will belong for one node for CPU, one node for memory, one node for block IO, and one node for network IO, and so on. So if you think about it, initially, when the system boots, there is only one node, and the first processes belongs to this node. So Even if you are not using containers yet, you are more likely to be using one big container with no limitation and no constraints. So then Farouk starts asking himself, it is a good idea actually to put a Java application inside a container, especially that the GVM offers a great number of benefits. The GVM is OS agnostic, is hardware and OS agnostic, and is runtime adaptive, which means that the GVM will try to tune itself and to adapt itself to ensure the best performance on the execution environment. However, Farouk decided to give it a try. And after reading a couple of tutorials, he came up with this Docker file. He built the image, he ran it, and the image is working perfectly. So easy peasy. But then Farouk asked himself again another question. What are the characteristics that my container should have and my production image should have? And the answer is basically three things. So my image should use a good base image that contains my runtime dependencies. And my image should be as small as possible. And my container, my production container, should have a fast startup. So let's discuss those three things. And first thing first, when we talk about good base image in the context of the Java application, we necessarily talk about the Java runtime itself. And I don't know if you have been following the Java news lately, but there were a huge discussion about in the Java ecosystem, especially after the new release cadence, which is 6 months, that we are not familiar with as Java developers, and the new licensing model that Oracle comes up with. But one of the great points and one strong point of Java, it's ecosystem, its community. So Java is self-free, and there are many providers that are offering Java for free. And even Amazon now, it's offering its own OpenJDK build, which is Amazon Corretto. And if you need support, there are many providers that are offering that as well. And the next thing we need from our container is to have a small image. And there are many techniques that we can use from both the Java side and the Docker side. So from the Java side, there is this feature introduced back in Java 9, which is Java Modularity or Project Jigsaw. And this feature enables us to tailor the GVM and select only the modules that we need during runtime. And also, it enables us to create our own custom GRE, putting the GVM in a strict diet. Techniques like code refactoring and code reviews helps to reduce the logic complexity, reduce the overall lines of code, and detect also if we are using a whole dependency to just a small utility function. And talking about dependencies, there are tools in the JDK itself like GDEBs and plugins available in both Maven and Gradle that enables us to detect the dependencies that we are effectively using and the zombie dependencies that are just sitting there in our runtime and we are not using them. So getting rid of those unused dependencies helps to reduce the size of our artifact and thus reduce the size of our final image. From the Docker side, however, there are many techniques as well. And we could start by using a small base image. And the smaller the base image is, the smaller our final image would be. Understanding also the principles of layering and caching of Docker helps to achieve that. And generally speaking, is it a good idea to combine the related comment into your Docker files and separate your related comments into it? Also cleaning up right away. And while working with Dockerfile, it is a common practice to download an archive, extract it, do some modification with the files, move maybe the directory in another place, and then forgot to remove this archive. So removing this kind of files, as well as some caching files and some log files, helps to reduce your final image size. Using Docker ignore, and it's something similar to git ignore, but it's for Docker. And depending on your application, you may want to ignore some kind of files, like the dot files, like the .get directory, or some log directory, or temporary directories. And using Docker ignore helps to reduce the final size of your image. And one nice side effect of using Docker ignore is it helps to speed up the build process, since the contexts, which are the file that are sent from to the Docker daemon are fewer. Also using multi-stage build, and this feature of Docker enables us to separate the build stage or stages from the production stage. And it keeps our production image, our final image, clean from the unnecessary build files. And finally, using Docker Squash. And Docker Squash is a utility function, a utility that that enables us to squash the image layers in order to generate a new image with fewer layers, while it keeps some Docker comments like the env and the port, so that the newly created image works exactly the same as the first one. And there is also an experimental option in the Docker build command, which is --squash, which does exactly the same thing. And while we mentioned using a smaller base image, one Linux distribution comes to mind is Alpine. And Alpine is a very lightweight Linux distribution. Its size is almost 4 megs. And it's based on BusyBox and muscle libc. Sorry. So, very briefly, BusyBox combines tiny versions of common Unix utilities into one single executable, and muscle libc is an implementation of libc as the standard C library, and this is basically the standardized interface between the user land and the kernel. However, one big difference between Alpine and other common Linux distributions that we are familiar with is that other Linux distributions are using glibc and not muscle. And that means that C and C++ code that is compiled with glibc will probably not work with muscle. And you may be wondering why we are mentioning C and C++ code in the middle of a Java session. And that's basically we, as Java developer, are using a software that has a lot of C and C++ code to do a lot of its work. And that is the GVM itself. So in order to ensure a transparent run of the GVM in Alpine and in muscle, some modification needs to be made in the GVM itself, in the code of the GVM. And luckily such project exists, and it's called Project Portola, and you can start contributing to it, and you can start playing with it as well as part of the early access of Java 13. And you may find on the internet many images that are based on Alpine, like the adopt OpenJDK images. And what these guys are basically doing, they are just adding the glibc Alpine package on top of Alpine. They are not using Project Portola on any muscle port on the GVM. And this slide gives a quick comparison of some Java images that you can find on the internet. And it shows clearly how the base image impacts the size of the final image. And the winner is clearly the OpenJDK JArray image based on Alpine, followed by two other images of Java 8 and Java 11 coming from Google Cloud Registry. And those images are part of a cool project from Google called Destroyless Container Image. And this project basically aims to create images that contain only the application and its runtime dependencies, restricting what's inside your container to exactly what your application needs to perform its function. So those images are built using Google Bazel tool, and it supports multiple languages, including Java, of course. And one other nice thing about this project is the base image they are using is a lightweight Linux distribution. Its size is almost 8 megs. And it's glibc based, which can be considered as a nice alternative to Alpine. And someone would ask, why should I care about making my images smaller? I mean, if it works, right? And the short answer is the smaller is better. And the long answer is everything in your container, in your image, is something that the provenance needs to be tracked and need to be scanned for vulnerabilities. And each time you are pushing and pouring an image, you are incurring costs and you are incurring expenses in terms of data costs and time. And finally, the smaller your image, the fewer components it has, and the smaller the surface attack, thus it's more secure. And the final thing and third thing we need from our container is to have a fast startup. And there is a common belief that the GVM has a slow startup, and that is true because the GVM, it's a complex piece of software engineering, and during startup, during running the application, the GVM does a lot of things. And the, the issue is now known, and the Java community made a huge effort to speed up the startup time and make it a lot more faster. And the easiest way to benefit from all this effort is to start using Java 11, as it has by far the fastest startup compared to Java 8, Java 9, and Java 11. Other techniques as well help to reduce the startup time, like class data sharing, ahead of time compilation, and a cool project from Oracle Labs called GraalVM. And this actually see that in action. So my project here is a very simple, oh, that's big, that's too big. It's a very simple niche application that starts a server, and then it returns, whenever it receives a request, it returns hello world, basically, nothing fancy about it. And what I do here is, just after the server starts in Bootstrap, I exit the application. So just to measure the time that the application took to start. And added also a shell script, and in this shell script, I'm measuring the time that the container took from the start to finish, and then measuring the image size as well. And this project is a multi-branch project, and each branch represents actually, okay, what it took that time. And each branch represents actually a feature that we can use either to reduce the startup time or to improve the image size. Okay, what's going on here? Okay, so each branch, as I've said, represents a feature that we can use to improve either the startup time or the size of our image. And the master branch, I call it the plain image, because it simply runs the application with Java 11 with no modification in the code and no optimization. So one technique we can use, it's called CDC, or class data sharing, and to execute a class file, the GVM does a lot of preparatory steps. So given a class name, it looks for this class name into the jar file, it loads the base code, it verifies the base code, and then it puts it into an internal data structure. This takes some time, and it is more noticeable during startup where the GVM needs to load hundreds or even thousands of class files. But the thing is, if the code inside the jar does not change, this data class does not change as well, and the application and the GVM needs to do the exact same preparatory step to come to the exact same results each and every time the application is run. So the idea behind class data sharing is to generate this data once, dump it into an archive, and then reuse it for future launches, and even share it between multiple GVM instances and multiple containers. And as you can see here in my Docker file, I'm dumping the classes that the GVM needs to load during startup, and then telling here that I need to dump this data into this archive. I'm calling it appcdc. And then for my production image, I'm enabling the class data sharing, and I'm telling GVM to use this archive during startup time. So that's one technique we can use to improve startup time. Another technique we can use is actually ahead of time compilation. And I don't know if you are familiar with JIT compilation, but ahead of time compilation is basically the same thing, but it's compiled ahead of time. So during runtime, during execution, the GVM collects many profiling data about the most executed code and compile it into native code. And that's enabled the GVM to create highly optimized code and improve the peak performance. However, during startup, the application and the GVM does not benefit from that, since the code is not yet JIT compiled. So the idea behind ahead of time compilation is to compile, to generate an ahead of time, to generate a library, and then compile the code into native code, and then tell the GVM to use this code that is pre-compiled. And to that, we use the GEUTC comment, and we provide it with a list of classes and method that we want to compile. And the file need to be in this specific format. It contains a prefix, which contains compile only or exclude, and the list of methods and classes that we want to compile. So using GEUTC comment, as we can see here, we generate a shared library, a library that we tell in my production image, in my file image, the Java to use this ahead of time compiled library in its in production. Another technique I mentioned to improve image size is Java modularity, and for that we use glink, and glink enables us, as I have mentioned, to select only the modules that we need during runtime in production and create our own custom runtime. So here I'm selecting only some modules, I'm creating my own custom GERE, and I'm running my final image. As you can see, I'm using the base image from DestroyList from Google, and I'm telling the GVM I'm using my custom GERE, which I'm called native runtime, and we'll see in the final the size of this image. Finally, I've mentioned a cool project from Oracle Labs, which is called Graal, and this morning it was a cool presentation from Chris from Twitter, who mentioned it, like using Graal, how Twitter uses it in production Graal, and he talked about the Graal compiler. And a GraalVM is basically a universal virtual machine of multiple languages, like for Ruby, JavaScript, and many JVM languages, of course. But what excites Java developers about this project is a sub-project called Substrate VM, and that enables to compile Java code into native code, just like we do with Go. And we generate this native code, so our application will run without need of the GVM. So our final application, this static file binary that we generate from using GraalVM, will run without needing of GVM. And as you can see here, so I compiled my final image. I'm using the latest release of Graal, which has been announced, I think, earlier this month. And I'm using native image and passing a bunch of options to generate my static library, my static binary of my application, and then I'm using Scratch. I'm not using any OS, if you noticed, and then I'm running this native static binary that I've generated using Graal. And if we actually go to run the benchmarking script, we will have some results similar to this one. So as you can see, compared to the plain image, if we are running using a GVM, AUT and CDC help it to reduce the startup time. And modularity, we're using modularity and using glink, our final image is five times more smaller than the original one. We're using the whole GDK, and we gain a lot of performance using GraalVM and Substrate VM. So the startup time, our final image, our application its size is under 10 megs, and the startup time is less than 80 milliseconds, which is great. So those were the techniques that we can use to improve startup time in the final image of our application. And then, as you can know, containers changed the way we develop, architect, and deploy our application to become the executable of the cloud. However, Furo thinks that containers added a new layer of abstractions, and was wondering if we can use the same good old tools that we are familiar with as Java developer to generate our archive, our jar files, war files, and EAR files, to generate this new unit of deployment, which is containers. And fortunately, there are many plugins available in both Maven and Gradle that enables us to do that. And the easiest way to achieve that in Maven is just like putting Docker comments inside Maven lifecycles by using Maven exec plugin. However, this solution is not so elegant. plugins. And other more sophisticated plugin exists, like Dockerfile Maven plugin from Spotify. And this plugin is the embodiment of simplicity, since it does basically two things. So it builds a Docker image from a Docker file and then publish it into a remote registry. Another more robust plugin exists, which is Fabric H Maven plugin from Red Hat. And this plugin enables us to do a lot of things, like creating images, pushing images, starting container, stopping container. It supports even Docker machine, creating volumes, viewing logs, and a lot of things. Other plugins exist in Gradle, and if you're using Gradle, there are many plugins that suggest more or less many features while working with containers. Another plugin from Google this time is called Xhub, and Xhub it's a pure Java plugin available in both Maven and Gradle, and it enables us to build our images, to publish them into remote registries without having a Docker file and without even having Docker installed in our machine, which can be considered as a great tool if you have to integrate it with your existing CI/CD pipelines. And what Xhub basically do is something similar to what's in this Docker file. So Xhub understands your code and split it into multiple layers and put in the layers that are less likely to change, and those are our dependencies and the resources files on the top, and the layer that are more likely to change, which is our code, our class files on bottom. And that helps to speed up the build process, especially incremental builds, and enables also to ensure reproducibility, since if the code does not change, the generated image will be the same. Another important thing while working in software engineering in general and while working with containers is image versioning and versioning. And for tagging your images, there are many techniques that can be used, and nothing stops you from combining those techniques. And one great benefit of tagging and versioning your image is you can at any moment in history detect how your application looked and how your container behaved. Another important topic while working with containers is security. And yesterday it was there were a great presentation by Scott from Microsoft about Kubernetes security. And talking about security and containers need a session on its own. And my goal here is just to give you some bullet points, some recommendations that you need to keep in mind while working with containers, starting with knowing what's inside your container. Especially if you are using third-party containers, you need to make sure that those containers are not downloading anything during runtime. Also, make sure that the application you are running scan it before. We're using SaaS source and vulnerability scanning source to make sure that there aren't any security issues or vulnerabilities in your dependencies that you are using. And while talking about vulnerability scanning, you can scan your image, your final image as well. And there are many tools that enables us to do that. And there are some free ones like Aqua Microscanner and Clear, using Docker Content Trust. And if you are not doing that at the moment, please start doing so. And while it is enabled, Docker Content Trust, the Docker daemon, when you try to push the image, the Docker daemon will automatically sign your image with your private key. So when a later user wants to pull your image, Docker daemon will automatically verify this image using your public key for authenticity, integrity, and many other things. Another important principle in security and software engineering in general, and especially in containers, is least privilege principle. And in the context of container, that means that we need to make sure that each process and each container and process are running with the minimum set of access rights and resources needed to perform its function. And there are many steps that can be followed to achieve that, like making sure that the processes running inside your container are not running as root. So even an attacker succeeds to exploit a vulnerability that does not give him a root access. Also, running your file system as read-only, so a hacker or an attacker cannot modify data or save malicious scripts in your container. And finally, limiting the resources that your container can use helps to avoid some kind of attacks like DOS attacks. Also, as I explained previously, using a minimal container OS helps to reduce the surface attack. And finally, having monitoring and auditing tools in place help to detect unusual behavior and trigger alerts if needed. Another integral part of software engineering in testing, and testing enables us to verify that the code we write works according to specification. However, and especially in integration testing, it is hard to build this real isolated and testing environment. And that's because our application needs to communicate with other services, need to communicate with databases, need to send email, and thus it needs some SMTP servers and so on and so forth. Containers help it to ease this process and help us to build this real isolated environment. And one library worth mentioning here is test containers. And it's a great library, the Java library, that has a couple of features, like it integrates easily with popular GVM testing frameworks like GUnit. It provides lightweight, throwaway instances of common databases. It offers port randomization, and my favorite feature is it automatically cleans up containers after the GVM shutdown. So with that, Feroz is confident and happy and wants to deploy his application into pre-production, and let's actually see that in action. So what I'm going, my application is basically a Spring Boot based application, which is a pit clinic application. Okay, which is a pit clinic application, and my Docker file is simply, I'm using Java 8 build number 121, and I'm just running my application with two options. Telling the GVM to show the options that it starts with during startup, and also I'm tracking the native memory, the memory that the GVM uses, but only as a summary. So let's start our application. So let's Docker run, and let's initially run the application with no limitation on the resources. So as you can see, the GVM started with almost 2 gigs of heap size, and that's part of the GVM ergonomics. And if no tuning parameters were passed to the GVM will set the 1/4 of the total memory as the heap size. And if we see the total memory available for Docker in my machine, Docker info, you can see here that almost 8 gigs is available, and the 1/4 of this value is 173 gigs. And the application started, and if we try to open it, I forgot to open the port. Okay. -p 8080. My bad. Okay. Good. And the application started. And it's simple Spring Boot application, pit clinic application with a nice interface. But when we talk about production, normally we use some orchestration tools like Swarm and Kubernetes, and that help us to manage our containers and also help us to limit the resources that our container can use. So let's simulate that actually, and limit the, let's limit the memory that my container can use and specify only 250 megs. And let's give it a name, and let's make it SBG8 250. And that's good. Let's run our application. Surprisingly, the GVM still thinks it can use up to 2 gigs of heap size, as the heap size. And it's completely unaware of the limitation and the constraint that I put into the container. And what happens is that the application will actually fail to start normally. Okay, so the application failed to start, and that's because the application or the container is using more memory than it's allowed to use. And if we see the docker inspect command, If we see Docker inspect, we can see that our container received an out-of-memory kill signal that bring the container into death. So we are Java developers, and when we have an out-of-memory exceptions and out-of-memory issues, what we do basically is we add more memory. So let's try to add more memory to our container, and that's it. So now the GVM still thinks it can use up to 2 gigs of RAM, 2 gigs of heap size. But now, how many of you think that this application will start? 0. Will not start? Who doesn't care? I do. So the application surprisingly started, and that will not happen in your production server since it has more resources. And the memory that the Docker can use is a lot more. So let's hit our application with some load. Okay, so it's AB. And what you will notice is that the application is somehow slow because it does not anything fancy. We are just requesting a simple get commands. And the application is doing a lot of input and output operations. So if we see the Docker states, you can see here that, where is that? Okay, and then, okay, so it's almost 530 megs for the read and 8 megs for the write. And that's a lot for a small application that does nothing. And let's actually see, if you remember, I've specified that I want to track the memory. And what I'm going to use is that I'm going to send diagnostic requests to the GVM, and I'm going to use a command called gcmd, which is a utility, which is a nice feature as a nice command available in the GDK, and it enables us to send a diagnostic request to the GVM about many things, like memory, GC info, Java flight record, and many things. And I'm specifying the unit of size as megabyte. And as you can see here, the GVM is using up to more than 1 gigs of as memory, and only the heap size is using around 800 megs, and that's a lot more than what I specified to the container. And the question is, from where the GVM got the other part of the memory? And the quick answer is that the application is actually swapping, and my container is using swap. And to prove that, I'm going simply to disable swap, and normally we do that in the host level, but if you are using containers, we can do that by specifying the swap memory as the exact value of the memory. So now, let's do the same poll. How many of you think the application will start? Still 0, will not start. Okay, you don't care. So the application will not start, and that's because it cannot get the additional memory that it will get in from swap. So let's get back to our slides. And our friend Fero is not happy now, since it's perfect application that was working perfectly in production, in local server and development server and staging server, failed badly in production, and starts wondering what are the elements, what make the application failed. And the first part of the answer comes from history. Like, the containerization movement started back in 2000 with FreeBSD jails and Solaris zones, and when Docker appeared in 2013, the containers technology exploded in popularity. However, Java, on the other hand, was there since 1997, and when Docker appeared, Java 7 was already out, and the work on Java 8 already started. And that explains somehow why the GVM is not container aware. Another part of the answer is, as I've mentioned, the GVM ergonomics. And this is a nice feature of the GVM, which using some information it collects from the underlying host, like memory, the number of CPUs, and other information. It tries to tune itself to ensure the best performance in the execution environment. However, if the GVM fails to get the correct values or get those values from the wrong place, these nice features become a nightmare. And that's exactly what happens with Pharaoh, as we have seen with the memory demo. And the same thing happened with CPU. So if the GVM fails to get the total number of CPU it can use, this will impact its internal threading pool. It will impact some popular Java APIs like the fork join pool and the stream API that we are using with Lambda expressions. And it will impact many popular Java software like Elasticsearch, Tomcat, and Nitti. So the issue is now known, and the Java community started the effort to make the GVM more container aware. However, if you are using Java update 121 and before, unfortunately the GVM is not container aware, and you need to pass the parameter by yourself. Or you can use something similar to a startup script made by the Fabric 8 community. And what these guys are basically doing, they are injecting a startup script that gives the information from C groups, from containers limitation, and then pass those parameters to the container, to the GVM, sorry. The first batch of features has been merged in Java 9 with the GC threads, and the JIT threads are now automatically set based on the CPU set CPU option. And for memory configuration, in order to be container aware, two options need to be passed. But unfortunately, those options are experimental, and good luck convincing your manager using an experimental option in production. A huge number of features had been added to Java 10 to make it more container aware, with more options that allow us more fine-grained control over the heap memory. And also a new formula has been introduced to calculate the total number of CPU, which is like the minimum of the CPU shares divided by 1024 and the CPU quota. In Java 11, more features has been added, like the container metrics and a new option to fix an underutilization option, which is the preferred container quota for CPU count. And this feature was specifically added to fix an underutilization issue that appeared with Kubernetes with the new formula of CPU calculation introduced in Java 10. So it is never a good idea to put an application into production without having metrics and monitoring your application. So from the Java side, if you're running a Java application, there are many tools available in the JDK itself and many tools from some open source and commercial providers. And if you're running your Java application inside the container, there are many tools provided by the Docker CLI and many community, open source, and commercial source that you can tools that you can use. So the final word, is it a good idea actually to put a Java application inside a container? The answer is definitely yes, because we benefit from all the features that the containers offer. However, keep in mind that the work to make Java more container aware is still in progress. And the easiest way to benefit from all the effort that has been made from the Java community to make the GVM more container aware is to start using Java 11, as it has by far the great number of features that make it more container aware. And keep in mind that Java has a rich ecosystem that offers more tools and libraries and plugins that make starting your journey for cloud native application, cloud ready application a lot more easier. And with that, thank you, and I'm ready to take your questions.